Have you ever wondered why today's powerful AI models are so gigantic and energy-hungry? It's partly because they use a brute force approach, pushing every piece of information through the same massive, fixed processing pipeline. But what if an AI could be more nimble? What if it could build a custom-made assembly line for every single problem it encounters, on the fly? That's the revolutionary idea behind a new concept called distributed neural architectures, or DNAs. This research tackles one of the biggest challenges in AI: the trade-off between power and efficiency. To solve this, the researchers created a model that isn't a single, rigid highway but more like a bustling city grid of interconnected modules. These modules are the standard building blocks of AI, like transformers that understand language or other parts that process patterns. The key innovation is the addition of smart routers that learn to direct traffic. When a piece of data, like a word in a sentence or a patch of an image, enters the system, the router looks at its content and context and decides the best path for it to take through the various modules. One piece of data might take a short, simple path, while a more complex one is sent on a longer journey through more specialized modules. Crucially, the model learns these optimal routes all by itself during its training process. This approach is a massive leap beyond current efficiency methods like mixture of experts, where data is simply sent to one of several specialized sub-models. With DNAs, data can take a complex, multi-stop journey in any order, creating a nearly infinite number of potential processing paths. The researchers showed that these flexible models perform just as well as traditional, dense models on both image recognition and language tasks. But the most fascinating part happened when they looked under the hood to see what the AI had learned. They discovered that the system had self-organized in remarkable ways. Certain pathways became highly specialized for specific functions, creating emergent, expert groups of modules without being told to. They also found that the choice of paths followed a power law distribution, a pattern seen everywhere in nature. This means the model developed a few super common highways for processing routine information and a vast number of rarely used country roads for handling unique or tricky data. This is an incredibly efficient way to organize a system. The model essentially learned to allocate its own compute power and active brain cells in a way that researchers could actually interpret and understand. Of course, this flexibility comes with its own challenges. The dynamic nature of these models can make them more complex to train and run on current hardware. Ensuring that some modules don't get overloaded with traffic while others sit idle is a key problem the researchers are already working to solve by building load balancing directly into the learning objective. This work pushes us to ask a profound question about the future of intelligence itself. Are we moving towards a future where AI doesn't just learn facts, but learns how to fundamentally restructure its own thought processes to better suit the world around it? If you enjoyed this breakdown, don't forget to like, comment, and subscribe for more AI research made simple.